Good morning. I'm going to be talking about some work that was done at the Naval Research Laboratory on acoustic vector sensors, with a specific focus towards trying to move it towards the size of fiber laser hair sensors. The motivation for our work is obviously naval applications. There's a need for miniature, high-performance underwater vector sensors, particularly at low frequencies. Vector sensors provide directionality, which means we can remove the left-right ambiguity in linear arrays, and also we can obtain higher array gain for the same number of scalar sensors. The aim for our development is to build vector sensors with low noise performance, reduced size and weight, and high reliability, which means for us no electronics in water. And in order to move away from electronics in the water, we focused on fiber lasers and optical fiber sensors. This is an outline for my talk. First, I'll discuss our approach, which is to use cantilever acoustic sensors. Then I'll talk about our design. I'll show some response measured in air. And then I'll discuss the effects of viscous fluids and how this can actually help us improve the acoustic response of miniature cantilevers. And finally, summary and some future work. So our approach is based on the idea that a time-varying acoustic field provides pressure gradient. And this gradient produces a force on the cantilever. This force drives the cantilever so that the cantilever follows the fluid motion. And this is actually different from typical hydrophone, which responds to the pressure changes. In order to measure the movement of the cantilevers, we use low noise fiber lasers and measure the strain. Now, the problem with this is that as you reduce the size of your sensors and your cantilevers, you also move the fiber sensor closer to the neutral axis. And this reduces the response, basically for the miniature cantilevers. What we'll show is that using viscous fluid loading, we can offset some of the effects of this miniaturization and provide greater amplitude response and increased usable bandwidth. I'll discuss the sensors in more detail later, but conceptually we investigated two regimes of operations for sensors. The first is a mutually buoyant sensor. The entire thing is enclosed in a pressure-resistant housing. We have a fixed support on one end and a large mass at the other end. The green lines show where the fiber lasers are, and there's a narrowed region. So when this entire housing is driven by the liquid motion, the mass responds to that acceleration, and the sensor flexes at this narrowed region. The second regime is where we have a fixed support. That is, the support is stationary relative to the fluid motion, and the fluid motion only drives the motion of the cantilever. The mutually buoyant sensor, there's a series of pictures as we assembled it, consists of two brass rods, one slightly shorter than the other. The mass is 4 centimeters long, 88 grams, and the bridge region is made of garolite. Its diameter is only 1.6 millimeters. The brass rod has a diameter of 6 millimeters, and you can see in this end view schematic, we've cut notches on the sides so that we can install two fiber lasers orthogonal to each other and provide dual axis operation. Each one of these fiber lasers is then about 3 millimeters off of the neutral axis. And this is a picture of the assembly before installing it into the casing. And the entire thing is about 9 centimeters long. For the stick support sensors, we developed two different designs. The first is a planar cantilever, which is essentially the fiber laser soldered onto a thin aluminum ribbon. The ribbon is 3 millimeters wide, but only 50 microns thick, so it flexes along its axis. This puts the fiber laser at just 88 microns off the neutral axis. And in order to do multi-axis, we would just have this design orthogonally mounted. The other design is a cylindrical cantilever, which is basically just a fiber laser itself. This would be analogous to a hair sensor. In this end view, you can see we use a fiber which has an offset core, and we write the laser into that offset core. This moves the sensing laser about 20 microns off of the neutral axis. And the entire, the diameter of this fiber is only 125 microns. Now, in order to do dual axis, we can have multiple cores in use in this fiber. In this example, we only had one offset core, so we accessed this core by using an offset splice, and we recoded the entire thing to 480 microns. Since we're talking about vector sensors, first I'll show the directional response, which is measured at 100 hertz in air. And on the upper left here, you can see the rod-style mutually buoyant sensor and the two axes, the response along the two axes. And also on the upper right-hand side, you see the planar cantilever response. In both cases, the extinction is very good, greater than 40 dB. In the cylindrical case, we ran into a problem with the 480 micron recoat because it was so heavy that as you rotated it, it made the laser stop operation. We did try some other lasers where it was not an offset core, so we didn't have to recoat to such a large diameter. And we did demonstrate that we were able to get high extinction ratio, but in those cases, the core is actually more than 100 times closer to the neutral axis, so your response is much lower. We also measured these sensors on a shaker table. The rod-style cantilever has a response where you can see between about 100 hertz to kilohertz, you have a relatively smooth region where you can operate your sensor. Unfortunately, for the planar and the cylindrical, you start to measure some of the higher order motions of that cantilever. You can see the resonances perturbing in the area of operation. The cylindrical cantilever does have some damping from that thick recoat, but you can see it's still a problem because it's not a very smooth response. So what can we do? The idea is to use viscous fluid loading. When you have an incoming acoustic pressure wave driving the cantilever, the acoustic wave produces both a pressure force and a drag force. The drag force is actually out of phase with the pressure force. Both of these forces depend on the viscosity of the fluid that passes by. So by your choice of viscosity, you can actually make the drag force dominate the motion of this cantilever. In that case, the fluid velocity is actually driving the cantilever as opposed to acceleration. And more details about this work can be found in our Journal of Acoustic Society of America paper from last year. Just as an example of theory versus experiment, this is frequency response for cylindrical cantilever. I have amplitude on the left column, phase on the right column. Both theory and experiment are plotted. There are four different fluids that we tested, covering basically 4 orders of magnitude in viscosity. And you can see in all cases, theory and experiment match very well. And these results are discussed further in our Journal of Applied Physics paper from this year. So, coming back to our sensor design, we tested our planar cantilever in castor oil, and the cylindrical cantilever in olive oil. As you can see, the resonance peaks have been damped, and actually the overall magnitude remained unchanged. So this provided a relatively smooth region of operation from 10 hertz down to, or out to kilohertz. And so this is very promising, because then when we compare all three sensors, and comparing to the rod style, we'll look at, say, 100 hertz. The planar cantilever is moved closer to the neutral axis. Is reduced to, the distance to the neutral axis is reduced to just 3%. And in the cylindrical case, it's reduced to less than 0.7%. Yet the response from the planar is still greater than 10%. And the response from the cylindrical is still greater than 5%. So this is enabled by the fact that the small size of the cantilever and the higher viscosity fluid puts us in a low Reynolds number regime. And in this regime, you can get a higher response than you'd otherwise expect from the size reduction. In the case of planar, it's greater than 3 times, and in the case of cylindrical, it's greater than 7 times what you'd expect. We can also, I mentioned the fiber lasers. They provide relatively low noise. So we can also, from the characteristics of the fiber laser, estimate the acoustic resolution of the sensor. Again, just as an example, at 100 hertz. If we compare the performance of the rod style to C-state 0, which is the lowest C-state noise level, you can see that it's actually well below C-state 0. With the planar design, it's only about a factor of 2 higher. And with the cylindrical, it's within an order of magnitude. So, in summary, we've shown a path towards miniaturization of these cantilever sensors by utilizing this new understanding of viscous fluid loading at low Reynolds numbers. We showed the damped resonances and increased the bandwidth so that you can operate between 10 hertz and kilohertz. And we were able to offset some of the reduction in response because of the miniaturization by using the viscous drag force. What we need to implement is flexible sleeves, obviously, to enclose the viscous fluid. We've also demonstrated high-resolution, mutually buoyant sensors that operate from 100 hertz to kilohertz. And also, in that case, if you want to expand the bandwidth, you'll need to damp some of the resonance peaks. And finally, we need to find a robust way to couple to the offset cores. One, to eliminate the need for the thick recoat. And also, if you want to access multiple cores in the fiber, you can't just use the offset splice. However, in literature, there have been many techniques that have been demonstrated for coupling to multi-core fiber, and I've just listed a few of them here. And thank you for your attention.